This is a walkthrough, a working note on loop engineering, a term that surfaced in a single week of June 2026 from 3 practitioners at once. Adi Osmani named it. Loop engineering is replacing yourself and designing the system that prompts the agent instead. Here is the whole argument in 3 lines. First, it is not about doing the work better. The earlier terms, prompt and context and harness engineering, all assume a human at the keyboard. This one deletes that assumption. Second, once a loop runs itself, it makes generation almost free, and that shifts the entire economy of the work. What stays scarce is judgment. And third, the unsettling part. The same loop built by 2 different people can end in opposite places. By the end, you will see why. Let's start with where this layer sits. The 4 engineering terms are not replacements for each other. They are a stack, and each one mines something larger than the layer below. Prompt engineering mines one good prompt. Context engineering mines the whole window. What to retrieve, what to summarize, what to clear out. The harness arms a single run. Which tools, which actions, or when to load context, what counts as done. It arms one run, but it does not make that run repeat. Loop engineering sits on top, and its whole job is to automate the waiting for you. With the first 3 layers in place, an agent runs cleanly once and then stops. The loop fits it with a timer so it runs on schedule, spawns sub-agents for parallel work, and feeds its own output back as the next round's input. That change is one of identity. You move from operating the agent to building the thing that operates it. So what does the loop layer actually add? 3 verbs. 1. It runs on a timer. The loop wakes on a schedule with no button press from a human. 2. It spawns helpers. A single turn can split off sub-agents. One drafts a change, another does nothing but pick it apart in review. 3. And this is the subtle one. It feeds itself. What the loop produces becomes its own input next round. Yesterday's findings are written to a file, and this morning it reads that file and carries on. That memory across conversations is why it is a loop and not a one-off task run many times. This is the single most important intuition in the whole node, so take a moment with it. Picture one underlying bug. An agent misreads what a function returns. Watch how the same mistake costs more at each layer. At the prompt layer, you see the wrong answer immediately and rewrite the prompt. At the context layer, you notice and clear the window. At the harness layer, the agent may act on the misreading, but the run ends, the diff is visible, and you review it before anything ships. At the loop layer, that same misreading gets written into the state file, read back the next morning as established fact, and built upon across many turns. The cost of a mistake scales with the number of turns it survives before someone catches it. By construction, a loop maximizes the number of turns. Everything later, the evaluator, the human checkpoint, the budget caps, exists to shorten the distance between a mistake and its discovery. The word loop is easy to misread as idle spinning. It is not. Each turn does something concrete, and it breaks into 5 moves. Discovery. The loop finds this turn's work on its own, rather than being handed a list. Handoff. It moves the task into an isolated workspace where the agent can change code without stepping on anything. Verification. A separate agent checks the result and is allowed to say no. Persistence. The result is written to state that survives the conversation. And scheduling. The loop wakes itself to do it again. Drop any one of these and the loop either will not turn or turns in place. The hardest and most important is verification, because it is the only move that can stop a bad turn from becoming permanent. Here's what those 5 moves look like in a real loop that one engineer runs. In the morning, an automation kickoff on its own. A triage skill reads yesterday's failing tests, the open issues, and recent commits, and writes its results to a markdown file. For each finding worth doing, it opens an isolated worktree. One sub-agent drafts the fix, a second reviews it against the project's task. A connector opens the pull request and updates the ticket. Anything it cannot handle goes to an inbox to wait for a human, and a state file survives so tomorrow picks up where this one left off. Notice the shape. No step needs a hand, yet the loop stops to wait for a person at exactly the point where judgment is required. That is a well-built loop. If the moves describe what happens in one turn, the parts describe what must be in hand for it to turn at all. Automations get the loop moving on their own, hanging off a schedule or a trigger. Work trees are a built-in Git mechanism that give each parallel agent its own working directory, turning parallelism from runs but messy into runs clean. Skills make project knowledge permanent in a single file, so the agent does not rederive context every turn. Connectors hook the loop to the outside world over the model context protocol. The issue tracker, the database, a staging API. Sub-agents split the one that writes from the one that judges. Counterintuitively, that is easier than getting one agent to be hard on its own work. And memory's persistent state on disk. The agent forgets when the context window clears, the repo does not. 6 parts, and a loop has a skeleton. The hardest part of a loop is not getting the agent to run. It is putting something inside that can say no, and the agent writing the code is the one least likely to say it. Ask an agent to grade what it just produced and it praises it, even when a human can plainly see the work is mediocre. This is not a smarts problem, it is grading your own homework. The window the code was written in is already full of the reasons it was written that way. So the agent sees the chain of self-persuasion, not the result. The fix is structural, not a matter of wording. You cannot ask an author to step outside its own perspective, but you can swap in another agent with entirely different instructions. A different model that assumes the code is broken until proven otherwise, and it should act, not just read. Point it at a browser, let it click the button and inspect the page. So judgment rests on does it run, not does this look right? In Cloud Code, the /go primitive runs until a fresh model agrees the condition holds. The failures are more instructive than the successes, and there are exactly 5 because each one is a single move. Skipped. Skip verification and you get the nodding loop. Every turn produces self-approved output and plausible mistakes pile up at machine speed. This is the most common failure, by far. Skip persistence and you get the amnesiac loop, which makes no cumulative progress. Each morning starts from the same place. Skip scheduling and you get the manual loop, a script a human runs by hand and then forgets to run. Skip discovery and you get the blind loop, where a human still spends every morning deciding what the loop should do. And skip handoff under parallelism, and you get the tangled loop, where several agents change the same directory and the merge is the mess no one can untangle. 5 moves, 5 ways to fail. That's Sam's skeleton scales. For an enterprise example, take a pipeline at Stripe that merges more than 1,300 pull requests a week, none written by hand. The trigger is lied, a message in Slack, or an emoji reaction. What makes it reliable is the stretch before the model wakes up. A deterministic orchestrator first assembles context, scanning links, pulling tickets, locating relevant code. Letting the language model find its own context is the least controllable part, so that work is taken out of its hands. The agent writes code, a hard-coded linter gate runs that the agent cannot skip. The agent fixes the lint, and a hard-coded step runs the commit. The counterintuitive lesson is that this is not built on a stronger model. Its reliability comes from the quality of the constraints, deterministic gates interleaved with creative steps. And notice, a human still reviews those pull requests. The person did not leave. They changed desks from writing to reviewing. A loop that runs itself is, at the same time, a loop that makes mistakes by itself, and 4 costs accrue quietly while it runs. Verification that is unverified output piling up in the gap between runs and write. Comprehension rot is the codebase growing while your mental map of it stalls, because reading code is more boring than writing it. Cognitive surrender is the attitude version. You stop having an opinion and just take what the loop hands back. And token blowout is the one cost that hits the bill directly when an idle bug spins all night and runs round after round. The point is that these are not a list of independent risks. They are a single failure that wears 4 faces and they reinforce one another. The more output goes unverified, the less you understand. The less you understand, the more you surrender. The more you surrender, the longer it runs unwatched, and the bigger the bill. The guard against all 4 is the same. Stay a person who can say no and install a checkpoint where that no can land. That brings us to the economic claim at the heart of the node. When a resource becomes abundant, its price falls and the work reorganizes around what stays scarce. Loops make code, plans fixes, and pull requests abundant. A single engineer with a good loop can produce the output of a small team. The typing and the boilerplate collapse towards 0 cost. What stays scarce is judgment. Knowing which plan is right, which line should be stopped, which output looks reasonable, but it's actually wrong. Loop engineering does not devalue judgment. It strips away everything else and leaves judgment as all that remains, and that is why the same loop built by 2 people can end in opposite places. The loop is a faithful multiplier. Bring understanding, and it amplifies understanding. Bring laziness, and it amplifies laziness. It is a faithful multiplication sign, and what it multiplies is the person. So how do you start? A first loop should be so small it barely looks like a system, a little thing that checks something on a timer. This 6-element checklist is the whole skeleton, scaled down. The first 2 elements decide whether the loop can run at all. A discovery source it reads on a timer, and a state file that holds memory from one round to the next. The other 4 decide whether it gets into trouble once it does. An evaluator that can say no, an isolated work tree per parallel agent, a token cap with someone who stops it, and a human review point that pauses for you to look. Beginners most often ship with only the first 2 built, and the result is a loop nobody watches and nobody can stop. The advice is simple. Start small, but with the no saying check and the human review point fully installed. Add parallelism last. After the checks have proven, they catch real mistakes. Across the whole node, the argument comes down to one sentence. Stop prompting the agent and design the system that prompts it instead. But there is a second half, and it is the half that decides where you land 6 months out. Build that system like someone who intends to stay the engineer, not just the person who presses go. The loop is the most powerful tool in this generation of software practice precisely because it is the most faithful multiplier of its builder. A faithful multiplier is exactly as valuable or as dangerous as the judgment fed into it. The playbook in the end is less about building loops and more about remaining the kind of engineer who can still answer on any given morning whether the thing the loop just did was actually right.